Thank you all for coming. You all know me. This is all the Aoml crowd. I'm going to be talking to you about work that I did for a paper in climate dynamics, and here are all the co-authors for the paper. Basically, over the past few decades, we've learned a lot about the structure of the zonal currents, so the equatorial undercurrent, the south equatorial current in the tropical Atlantic. But with those observations, very little has been studied about the meridional flow. So what is the structure of the meridional flow? So the goal of the study is to describe the long-term mean meridional velocity structure in the cold zone region, so in this region here, specifically along the longitude of 23 west and 10 west, using observations, so using drifter, Argo measurements, moored velocity measurements, and shipboard and lowered ADCT measurements, and also from Reanalysis products. The second goal is to look at the differences between the seasonal means. And by that I mean a 6-month mean in December and May, and June to November. And those time periods are of interest because during December to May, the trade winds are weak, and the cold tongue, which is this region of cold water, is absent or very weak. And then in June to November, the trade winds intensify, and the cold tongue is very strong. So this is showing you a map of June to August sea surface temperatures, and you can see that the cold tongue, the region of cold water, is present and very strong. Okay, that's not working. Okay, why do we want to look at the long-term mean structure? As I mentioned before, we don't know very much about that structure. And we know from the western equatorial Atlantic and the tropical Pacific that in the upper 100 meters, the flow near the equator, the meridional currents, are dominated by these shallow overturning cells that we refer to as tropical cells. So this is a schematic from a paper by Bob Molinari in the western equatorial Atlantic. And so the tropical cells, you typically have upwelling at the equator, and then because the trade winds are blowing from east to west, you tend to have poleward flow at the surface. So it's the north of the equator to the south of the equator. You tend to have downwelling between 3 degrees latitude and 5 degrees latitude. And then return flow, so equatorward flow below that. And that's driven by geography. So that's driven by zonal differences in the pressure gradient. These tropical cells are embedded in strong zonal flow. So you have the equatorial undercurrent that's coming out of the page. You have at the surface the south equatorial current that's going into the page. So these are not really, these are not there in isolation. You have strong zonal flow in addition. And they are also part of these larger overturning cells known as the tropical cells. Okay, but we don't really know what this looks like in the cold tongue region, so that's the idea. We want to look at 23 west and 10 west and see what the structure of these cells looks like. Why do we want to look at seasonal differences? Well, during June to November, when the cold tongue is present and the trade winds are strong, tropical instability waves are also present and quite intense. And their impact on the seasonal means is not well known. And I'm showing here all of the cruise transects along 23 west, these first three, and along 10 west. So this is latitude and depth. All of the transects are reflected in June. And what you can see is this is an unusual instance where there were 2 transects collected right after each other, a week apart. And it's during a time period when you have tropical instability waves passing through. And you can see that the flow south of the equator on the 19th of June was all southward and very strong. And the flow 1 week later was all northward and very strong. So these are very intense. These impact the circulation quite a bit, and it's hard to determine just from these 2 plots what the mean, what the background would be. So it's completely obscure to me. The other thing, if you don't know about tropical instability waves, is they have periods on the order of 20 days to 40 days. They have wavelengths on the order of 1,000 kilometers. So that's approximately the distance between 23 west. It's just under the distance between 23 west and 10 west. You can see that this transect, which was on the 26th, and this transect, which is on the 27th, look very different from one another because the tropical instability waves are in that region. And so, 15 degrees upstream looks very different from 15 degrees downstream because you have tropical instability waves moving from west to east. Also, during this time period, we care about the seasonality of the currents because you can have interannual anomalies, specifically in boreal summer and fall. You can have warm temperature anomalies that develop just north of the equator. And if the seasonal flow is stronger during that time, then you're better able to advance those anomalies southward and impact the equatorial region. And in the case of this study, these two studies here, you can create a non-canonical Atlantic El Nino event if you create a warm anomaly that's downwell and then advanced towards the equator. In the case of 2009, there was a cooling event. So in that case, you develop cold temperatures here. And that is a potential mechanism for those cold anomalies to make it to the equator. So that is the reason why we want to study these tropical cells. Okay, so I'm going to construct means from shipboard and lower ADCP sections that were collected in the tropical Atlantic along two primary lines, along 23 west and 10 west. And this shows pretty much the standard transects. These data were collected under the umbrella of various field programs. There was Parada, there was CASE, Aoml, EG, BNDS, all with different goals and all on different ships. So the cruise tracks are not the same for each section, but there's sort of a common cruise track, an overlapping cruise track that most of them observed. So you can see here the timeline. Along 23 west, we have 36 cruises. Along 10 west, we have, along 23 west, we have 36 cruises. Along 10 west, we have 19 cruises. And these field programs also deployed mooring, so we have also moored measurements of velocity. And so you can see here that along 23 west, the black lines indicate where there's moored ADCPs. They're typically, measuring, they're typically mounted at about 200 meters, upward looking, resolving the flow in the upper 200 meters or so. And then the red symbols show you where there are fixed depth current meters. So we have a handful of fixed depth current meters at 10 meters depth, or in one case at 20 meters depth. And these show you the timeline. So the black are the moored ADCPs, and the red is the fixed depth current meters. So we have all of this wonderful data at our disposal. Now the cruises, even though we have cruise data for every season, so this shows you 10 west, and then the light gray shows you 23 west. We have cruise data in every season. There are seasonal biases to when the cruises were tended to happen. The majority of the cruises along 23 west were in the spring, the boreal spring, and the majority of the 10 west cruises were in the summer. But if you look at the 23 west cruises, if we pull together the December to May cruises and the June to November cruises, we have almost an even number of samples. We have 21 in the first time period and 16 in the second. So we can do this partitioning into 6-month means that I'd love to do, and look at time periods when the cold tongue is absent or weak, and the time period when the cold tongue is present. Unfortunately, there aren't enough samples at all along 10 west, and there's also not this even distribution. There's not very many samples in December and May along 10 west, so I can't do the same thing. There were some challenges that we had to override in processing all the shipboard data, and I'll kind of walk you through that. First of all, most importantly, the shipboard ADCP data and the velocity measurements above, there aren't very many above 30 meters, and that has to do with the configuration of the configuration of the lower ADCP and shipboard ADCP measurements. So we need to extrapolate to the surface. We really want to look at what the meridional fluid looks like at the surface. So we have to extrapolate upward using near surface velocity from other data sets. And the primary one that we use is a combination of drifter and Argo surface float data. So the drifter data is providing you an estimate of the currents at 15 meters. And the Argo floats, when they come to the surface, that data is collected, and while they're at the surface moving around, that data is collected. And from that drift, you can also estimate the velocity. So that I'm going to refer to as ADCP plus V when I extrapolate upwards to the drifter Argo float data. And then to see if it's sensitive to what product I use, I also extrapolate extrapolate upwards to the Oxford data, and that's cleverly ADCP plus O. The other issue is that, as I said, there's sampling biases, there's not very many samples, despite the fact that we do have 36 cruises and 19 cruises, which is actually quite a lot for one particular region. It's still important to estimate the uncertainty because we can very easily compute the mean, but how significant is that mean? Also, the other thing that we do is we compare against the available more data. So we have all of that more data, so why not use it to try to see how significant the ADCP means are? And then we have at our disposal a global ocean reanalysis product, and so we are also going to use that to evaluate the means. So the Oxford data, it's a weekly product, and it's computed from satellite. It feeds in a lot of satellite measurements and produces a weekly current measurement at 15 meters depth, or you can think of it as a depth average of the upper 30 meters. And we have that weekly from January 1993 to December 2011. And then, as I said, we have this more data, and unfortunately, only at 3 of the locations do we have any data in the upper 30 meters. So we have this wealth of more current meter data, but very little of it is in the upper 30 meters. But we'll do the best that we can with that data. Then, as I said, I'm going to use GLORIS, which is a global ocean reanalysis. It's available on a quarter-degree grid. It has very high vertical resolution. And the benefit of this product is that it assimilates satellite sea level data at FFT, and it assimilates Parada temperature and salinity data. So it's not reality, but to the extent possible, it agrees quite well with the Parada data. So it can help us to interpret the means that we observe. And I have daily fields from 1993 to 2009. Okay, this is everyone's favorite part, the methodology section. I'll try to go through it as quickly as possible. This was work done by Verena when she was here, and I will describe it as best as I can. What we did was we took the shipboard and lowered ATP current. So as I said, they're all on different grids because each cruise serves a different program, and with different, on different ships. So the resolution is not always the same, and the depth range is not always the same. But they have this common, region of 30 meters to an intermediate depth of 250 meters. Not all of the cruises have hydrographic data, so when I average together all the shipboard data, I do it in depth coordinates. If I had hydrographic data for each cruise, I could average in isopycnal coordinates, which has been done in other studies, but we don't have that data. Okay, so we get the lowered and the shipboard ADCP data, and we merge them together with respect to the higher accuracy of the shipboard data. But the reason why I don't entirely discard the lowered ADCP data is that, for example, in January, along 23 West, I don't have any shipboard ADCP data. So to not throw out, to increase the density of the data and have better coverage throughout the year, it was important to include the lowered ADCP data. I take the 30-meter ADCP data, and I extrapolate upwards using the mean near surface current. Then what was done was all of the data is mapped onto a uniform grid, so 0.05 degrees in 10 meters bins, using a Gaussian interpolation scheme. We could have used, in previous studies in the tropical Pacific, they took the ADCP data at 30 meters and 40 meters. They estimated a shear and extrapolated upwards. We could have done that, but the problem is that in the tropical Atlantic, if I use the 30 to 40 meter shear and I extrapolate upwards, the surface currents north of the equator are southward, whereas if I use the drifter and Argo data, it's northward. And again, if you have trade winds blowing from east to west, you expect the flow to be northward. So using shear between 30 and 40 meters is not a reasonable thing to do. However, you will notice that if you do the same thing with zonal velocity, there's not much sensitivity to which product or what assumption we make. And so in that case, what was typically done is based on zonal velocity, and that's not a sensible thing to do for meridional velocity. Okay, so instead, we're going to extrapolate upward to mean 15-meter currents from the drifter Argo flow data. I'm not going to go into all the details here, but there's not much tropical data from drifters because the drifters just don't want to stay on the equator. So if we use the global product that the drifter group has put out, that RIP has put out, if we discard drifters that have become undrove, we would lose about 30% of the data. So what we do here is we correct all the available data. We correct the drove drifter data, the undrove drifter data, and the Argo surface flow data using a flip correction. And that flip correction varies for each of those three categories. But basically the idea is we didn't want to throw away any data because the drifters, otherwise there's just not a big enough sample in the equatorial region. So the drove drifters account for about 68%, and the undrove 24, Argo 9. Obviously I'm rounding that because that doesn't add up to 100. But anyway, once we put all of this together and we correct each of those components, we put them all together and try to get a mean estimate of the 15-meter current. And we do that by, at each grid point, we interpolate this onto a uniform grid. And at each grid point, we fit to a model that has a time mean value, annual and semi-annual harmonics, and linear trends corresponding to the distance from the center of that bit. And then it's this time mean value that I say is my mean velocity from the drifter Argo data. And that is what I'm going to use to extrapolate upwards to the surface. Before I show you the means, I can say a word about the uncertainties. So below 30 meters from the ADCP data, the uncertainties are simply the standard error of the mean from the ship-based ADCP velocity estimate. And I assume for that calculation that each cruise represents an independent sample. So I'm showing here the number of samples that I have. So this gray line shows you 250 meters depth, 30. The blue shows you 300 meters. So you can see that the number of samples varies with depth and it varies with latitude. And that goes into the standard error calculation. But when you look at the standard errors, you see that most of the errors are in the upper 100 meters. And I'll show you in a few slides that has more to do with the variability of the velocities than the variability in how many cruises I have. With the exception of some places, down here between 200 meters and to north, obviously there's no reason to expect you to have a strong physical variability here, and that probably has much more to do with the fact that the number of samples dramatically drops off there. Above 30 meters, what we do there is different. For the drifter Argo measurements, we have an estimate of that error. And so what Verena did was she ran the extrapolation and the Gaussian interpolation with the drifter means, and then she just added an error proportional to the drifter error. And she did that 1,000 times. And so the uncertainty in the upper 30 meters is just the 2 times the standard deviation of all of those realizations. So it's a little bit different what we did in the upper 30 meters. And I can tell you plenty more about that if you want to ask me about it. Okay, so now we can get to the exciting part, which is the mean field. And I'm showing here, before I say anything else, the mean field, and wherever you see dots, that indicates where the means are greater than the standard errors, so where they're significant. Okay, so the first thing you notice, or the first thing I noticed, is that you do have, at 23 west, this is now place west in Headland, you have poleward flow. And what you notice right off is that the northward flow in the northern south, so north of the equator, is stronger than it is in the southern south. And it's also shallower. The northern south, the surface limb of the northern south is contained within the upper 30 meters, whereas the southern south, the surface limb is about 50 meters thick. Okay. Now, if we look at the same thing at 10 west, it's more symmetric at 10 west, but the thickness of the cells has deepened slightly, and the flow is just less symmetric. But you have the same pattern. You can have northward flow and southward flow. But the transition between the northward and southward flow isn't lost on the equator. This dashed line shows you where the equator is on this section. And this dashed line shows you on this section. So you notice it's south of the equator where you transition from southward to northward flow. And as you move from 23 west, that transition is further southward. Also, the location of the maximum in the north of the equator and the maximum north of the equator here moves southward, as we move from 23 west to 10 west. The other thing, which maybe is not so apparent, but, well, I've already said it, is that the thickness of the cell has decreased. But I think it's more apparent when I show you the model velocity. Before I show you the model velocity, I just want to say that the equatorward flow, so here, 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 and here, is a lot weaker than the surface flow. And unfortunately, even though it looks reasonable here at 23 west, this obviously jumps out right at you that you switch from equatorward flow, from northward flow, to southward flow here. And this looks artificial, and it kind of overlaps with where you have a drop-off in data. So it's unclear whether it's physical. And then the other problem is that the signal is so small here that it's not significant, given the standard error. So none of this area right here has gray dots on it. So if we look at the same thing for the model, you see, looking at the surface circulation, again, the transition between the two cells is south of the equator. You have stronger flow in the northern cell, and the transition between southward and northward flow shifts further south of the equator from 23 west to 10 west. The other thing that you see in the model is that the equatorward flow is weak in the model, as you expect it to be, and agrees with the observations, but it doesn't really look like the observed structure. So the question is the model wrong, or is it just that we don't have enough observations to really constrain that subsurface flow? And then below 100 meters, the flow is very weak in both the model and observations, and is even less alike than. So there's some caveats to using the model product, but I think that we can all see that in the upper 100 meters or so, there's a lot of agreement between the model and the observation. Okay, so as I said, the cell in the north is about 30 meters thick. The cell in the south is about 50 meters thick. So one can integrate through that cell to estimate the transport. So if we make a box between 23 west and 10 west, and we integrate the velocity downward, we can estimate the volume transport. Okay, so the black line is from the observations, and the left panel is integrated to 30 meters, so it's the thickness of the northern cell, and the right panel is integrated to 50 meters, the thickness of the southern cell. So you see that in the north, the transport is maximum when I integrate 30 meters, and is about 2.3 spurges. In the southern cell, the maximum transport is found when I integrate to 50 meters, and it's about double of that. So even though the surface flow is stronger in the northern cell, the transport is stronger in the southern cell, and that has to do with the thickness of the southern cell. It's much thicker. The thick blue line is the same transport computed from the modeling product. So you can see that the transport in the model is very similar to the observed transport, with less transport in the northern cell than in the northern cell, and then in the southern cell. And the other thing that the model gives us that the observations don't is that I can compute the transport as I did for the observations, which I just averaged the velocity at 23 west with the velocity at 10 west, and then multiply by the distance between the two to estimate the transport. So it's like a box transport calculation. But in the model, I can actually integrate between 23 west and 10 west because I have all of those points. And that's what this line with the dots is. So at a few latitudes, I computed the actual integrated transport. And you can see that those two agree well. And what that tells you is between 23 west and 10 west, the velocity varies fairly, the mean velocity varies fairly linearly in that region. And computing the transport using all the values inside from 23 west to 10 west is the same thing as if I just have the endpoint. Okay, so now what is the variability associated with all of those cruises? As I said before when I showed you the standard error, most of the variability is in the upper 100 meters. And the same thing is true in the model. Okay, and they look quite similar, so that gives me some feeling that I've captured quite the range of variability with the available transports that I have. There's also the same tendency to have the strongest variability at 23 west in north of the equator, and it extends furthest downward when compared to the other longitudes. And this higher variability north of the equator has to do with the fact that the winds are more variable north of the equator. So you have the IPCZ region, and you also have tropical instability waves that tend to be stronger north of the equator, and you also have intra-seasonal variability, so like 14-day timescale variability and 2 to 14-day variability that tends to be stronger north of the equator. So that's why physically you have more variability north of the equator. Right. Well, that's all wonderful, and now we can see, we have these ancillary data sets that we can use to sort of get an estimate of how good this extrapolation with the ADCP plus V is. And so this is showing you the velocity of the function of latitude at 10 meters at 23 west, 10 meters, 10 west, and then at 20 meters depth, 23, 10 meters depth, 20 meters depth, and 10 west. The ADCP plus V is the solid black line. The ADCP plus O is the extrapolation to Oscar. The blue line is the model. The red line is where we have current meter data from those fixed depth current meters. And the green symbol is the upper bin, the 20-meter bin of those handful of moored ADCPs that have actual velocity data at 20 meters. Okay, so did you notice the similarities of the differences, whichever your eye is drawn to first? I noticed the similarities, and so what I think is really interesting here is where we have independent velocity to validate against, they're all the same. They're very different, and there's no independent in situ data in this region or in this region to say which one is best. So unfortunately, we need a lot more moored measurements to be able to really get a handle on what's happening in the upper 30 meters. But I will say that the extrapolation to Oscar, the dash line, is obviously wrong because you don't expect to have northward flow south of the equator. You expect to have, because of trade winds going from east to west, you expect to have southward flow. So that's a caveat. Even though the Oscar product is great in other places, the buyer should beware when looking at mean meridional velocity in the Atlantic region. But they all agree quite well where we do have the observations, and obviously, if there had been a mooring here, I could say more about that. But what we do have is at a variety of locations we have velocity profile data. So even though there's not much data above 30 meters, there's lots of data below 30 meters. So here I'm showing all the mooring data, with the green line, from all the moorings at 23 west and all the moorings along 10 west. So you're moving from south to north and south to north. And then these line up. So these are both at 3/4 of a degree, at 0 degrees, and at 3/4 of a degree north. So what I want, there's a lot of information here. That the green line is the moored ADCP data. The red symbols are the moored current meter data. The black line plus the arrow bars is from the shipboard ADCP. And the blue is the model. So what I want to focus on is the region where the moored ADCPs don't agree well with the shipboard ADCP estimates. And that happens near the equator, here between 50 meters and 250 meters, and here between about 75 meters and 150 meters, and then also in this region. So there's everywhere else, they agree within the uncertainty. So there might be disagreement, but they overlap within the uncertainty. But these particular regions where perhaps the shipboard ADCP measurements are not sufficient to remove all the mesoscale variability, these are the regions where they don't agree to any uncertainty. Okay. If I do the same thing with the model, so now I'm going to compare the moored ADCP data with the model. Where those don't agree is at 0 north and 10 west. So in the region where you have the equatorial undercurrent, the zonal flow is dominated by the equatorial undercurrent. The model more quickly with depth goes to 0 than the moored measurement. So all the other places, they overlap within the uncertainty. And I'm just showing you where they don't. So that tells me that given the available data that I have to validate the ADCP plus D means and the model, that's doing pretty well. And now we can turn to the second goal of the study, which was to look at the difference between the seasonal means. So again, when the cold tongue is absent and when it's present. So when it's warm and when it's cold in the cold tongue region. And for the morning data, it's gappy. It's not. I don't have 3 exact years of data or 4 exact years of data. So I built an annual cycle using the data, and then I used that annual cycle to estimate the seasonal mean. And I did that with the drift short data as well. So basically, I took the model and I can tell you more about it. But the other thing to remind you of is that there's not enough cruise samples along 10 West to examine the seasonality below 30 meters. We can certainly do it from the drifter data and the model and from the moored data, so I'm going to do that, but there's not enough data to do it from the cruises. Okay, so this is all at 23 West, near surface currents. The left panels are December through May. The right panels are June through November. The blue shows you the seasonal mean, so this is the December to May mean. The blue is the June to November mean. The black shows you the annual mean for reference. So the first thing that the puzzle that we see here is that in June through November, the trade winds are supposed to be strongest. So the near surface currents, one would expect to be stronger during that time period. And you can see from the blue line that they're stronger in December to May when the trade winds are weakest. That's a big puzzle as to why that's happening. And that is something that happens in both the observations, so this is drifter Argo, and in the model. You have this reverse seasonality of what you expect to see. And the way we can understand what's happening with that is if we break up the model near surface currents into the geostrophic part and the ageostrophic part, just the difference. So I do that, and what you can see is the dashed line is the geostrophic part. There's more seasonality in the geostrophic current at 23 West than there is in the ageostrophic wind-driven current. So even though the winds are doing what they're doing, and you expect them to give you a stronger flow in June to November, which they do, this component is just a wind-driven part, the variability of the geostrophic current is opposing it and winning. So at 23 West, you have reverse seasonality of the surface flow than what you would expect to find. If you look at 10 West, though, you get what you expect. You expect that with stronger trade winds, both in the observations and in the model, you have stronger poleward flow in June to November. And that's because at 10 West, the seasonal variations in the geostrophic component of the velocity are not very strong. There's not much difference between the geostrophic components between those two seasons. But there is a very strong seasonality in the ageostrophic component. So at 10 West, the winds win, and at 23 West, the geostrophic circulation wins in terms of the seasonality. I forgot to mention, and I'm jumping back to show you that, that also you have in the seasonal comparison, you have the transition from southward flow to northward flow shifting southward when you go from December to May to June to November. So in June to November, the transition between southward and northward flow is further south of the equator. And that happens at 10 West also. You can see that here. I think it's a little bit easier. You have the transition happening here almost on the equator, and then in June through November happening further south of the equator. And we can understand that through the winds. This is showing you now the wind-driven response. This is the Ekman-like transport. So this has been modified for the equator. But this is the wind-driven transport given the model wind for December to May at 23 West, June to November 23 West, and then at 10 West. And you can see, like I said, this difference of stronger wind-driven flow in June to November and weaker wind-driven flow in December to May. But this also gives you a way, when you're looking at the mean circulation, so when you're looking at the black lines, this gives you a way to understand why the transition from southward flow to northward flow happens south of the equator. And it's because in this region, because you're using this equatorially modified wind-driven model, the winds have a southerly component. And the southerly component becomes more strong as you move from 23 West to 10 West. And it becomes more strong evenly. So that's why the transition happens south of the equator. Now we can look at the response below 30 meters in the ADCP data and in the model. And so what you see here is that the equatorward flow, the southward flow, becomes stronger in June to November. That's kind of what you would expect to happen, is that you expect the tropical cells to become stronger in June to November. And so you see much stronger southward flow in both the observations and the model, and particularly north of the equator. And I think this gives you another view of what I was saying, is that the surface flow is stronger in December to May, which is counterintuitive. You would expect that the whole cell would intensify in June to November rather than just components of it. We have the more data, and we can do the same thing with the more data. So here, blue is June to November, and red is December to May. And what you see is that the southward flow in June to November is stronger at T north than it is in December to May. You also see that the flow near the surface at 0 north, 10 west becomes more positive, which is indicative of the northern cell moving southward. So where you normally have 0 flow, you're starting to have positive flow because the cell has moved southward. The problem here is that the standard errors and the uncertainties are really large. And the only place that I think these differences in the mean, given the uncertainties, are significant is here at 0 north, 10 west. So clearly, more long-term observations are needed to say whether this is significant or not. The other thing is, we don't have velocity profile data at 4 north. And when I do the same comparison in the model, that's precisely where the model says there is the biggest seasonal difference. You tend to have very strong southward flow at 4 north, and you can also see it at 2 north. So even though the observations are not significantly different from 0 in terms of the seasonal means, they're consistent with what the model is telling you and what the physical intuition is telling you. And you also here see this shift of having more positive flow in the summer, more positive flow. So that indicates that that whole northern cell is shifting southward in the summer. Okay, so in this study, we're able to describe for the first time the long-term mean meridional velocity along 23 west and 10 west using in-situ observations, so using drifter, Argo, shipboard lower ACP, and more velocity measurements. We found that the dominant circulation feature in the mean meridional velocity are the tropical cells with near-surface poleward flow and subsurface equator shore flow. And that flow was stronger, and the thickness of those cells was shallower in the northern south. We also demonstrated that the thickness of the surface line decreased when you moved eastward from 23 west to 10 west. And the boundary between those two cells, the north-south boundary between those cells, moved southward from 23 west to 10 west. In terms of the seasonality, we found that the maximum flow in the surface line of the cell was stronger in December to May along 23 west. And that was because the geostrophic variability won out over the wind-driven variability. In the subsurface line, we found that the maximum southward flow in the northern cell was during June to November. So what are the implications of that stronger equatorward flow in June to November? During boreal summer, if you have seasonally intensified flow in that subsurface cell, any temperature anomalies that you're putting in north of the equator are going to be advected towards the equator, and then you can trigger these anomalous warming events on the equator. So if you have a warming event north of the equator, you can trigger a non-canonical El Nino event. If you have a cold anomaly, you can trigger the events that Bragg and Peter Brandt observed in 2009. And what I'm showing here is a complication of that. A further complication is that the tropical cells may be interannually modified. So this is showing you the mean velocity from June to November 2009. So it's just 2009 when you had a strong cooling event. And you see that you have a very strong tropical cell during that 1 year when you have a cold anomaly. So you have stronger flow than average, affecting that anomaly towards the equator. And what I'm showing on the right side is the difference between the June to November 2009 minus June to November for the whole 19 years of the model. So that, I think, further demonstrates the fact that surface flow, the poleward flow, is stronger and you have pretty much southward flow across the equatorial region. So if you put a warm or cold temperature anomaly here, it's going to be affected towards the equator. And the caveat obviously being is that this is from the model, and more observations are needed to be able to examine the robustness of this result, reduce the uncertainties in our results from observations. And specifically, between 1 degree latitude and 4 degrees of latitude, and in the upper 30 meters, where you have the strongest flow with the tropical cells, where you have the strongest flow with the tropical instability waves, and where we don't know much about the vertical shear. Fortunately, we were loaned very graciously by Libby and by Ryan and by Nelson 2 SOMTEC current meters, and we added those to the 4 North, 23 West moorings during the PNE 2013 B cruise. So this is a schematic of what the mooring looks like. Normally, there's a current meter at 10 meters depth, but we deployed those loaned current meters at 5 meters and 20 meters depth. So this will give us estimates of the shear in the upper 30 meters. And we also, here's a picture of what those SOMTECs look like. We also tested different configurations for the shipboard and lowered ADCP. Usually they use an 8-meter bin, and we tested 4-meter bins. The idea being to try to reduce that region where you can't collect data in the upper 30 meters. So trying to reduce it as much as possible and try to get another independent estimate of the shear. And then we deployed 20 drifters. So again, that's measuring the current 15 meters depth. So we tried to do as much as possible to observe as much as possible in the upper 30 meters. And this is some preliminary data. Fortunately, the way that these moorings are put out, so you can get daily data real time through their website. And then at some point, when this particular deployment is over, we'll have 20-minute data. But we have real-time data for 2 months data so far. So I'm showing you the zona velocity and the meridional velocity at the 3 different depths. When we sampled, we were in the middle of a TIW, which is rather late in the season to have a TIW in November and December, but it was really fortunate that we could do that. And so you can see the great level of variability that exists in just this 2-month record associated with this particular TIW. The other thing that you can see is when I compute the shear between 5 meters and 10 meters, the shear is not constant in time. And at 10 to 20 meters, one might say it may be constant in time, at least relative to the 5 to 10 meters. But stay tuned for what we learn about the shear on diurnal timescales and what we learn when we collect a full year's worth of data. And I should take a moment to say that should you have any spare current meters lying around, I know exactly where to put them, and we'll be happy to do that. If we look at the mean from that 2-month period, this is just another view of what the data is showing. You can see that the shear is not constant with depth either. So not constant in time, not constant in depth. So the assumptions that we typically make to extrapolate upwards are not valid, right? It's the best we can do, but they're not valid. So we also deployed 20 drifters, showing just the ones that were deployed near the equator, here. And we deployed them in drifter pairs. And this is just a weekly trajectory, so it's not showing the high frequency variability of the drifter pairs, the drifter trajectory. But what's really fascinating is that the 4 drifter pairs that were deployed near the equator all moved westward and all converged in this one region, in what I like to call a drifter party. And then they've now moved northward and are now being affected by the north equatorial countercurrent, and I presume there's another party going to happen over here. But we deployed in the middle of a tropical instability wave. This shows you what the temperature looked like around the time of deployment. And obviously, there was a lot of convergence associated with that. That TIW is investing westward. And obviously, there's a lot of convergence in the flow associated with that TIW. So it'll be really interesting to look at this in more detail relative to the position of the front and what the TIWs were doing. And if these drifters were not drove to 15 meters depth, if they were 3-dimensional, if they could move 3-dimensionally, likely they would be sinking here because of the convergent flow. This is just a quick view of the lowered ADCP meridional velocity, and just demonstrating once again, you can see this large meridional flow, which is on the order of 50 centimeters per second that we observed. So we were in the middle of a TIW because we have very fast flow. Remember, the mean flow is 10 centimeters per second, 15 centimeters per second, so that's the challenge when you're trying to estimate the mean. So I'd like to take a minute to thank various programs, funding agencies, and people. The field programs, there's various field programs, PACE, Aoml, EGE, VFDS, that donated this data to me. They were not using their meridional velocity data, and I happily collected it all to work on it. So all of my co-authors and the various people working with them helped me with preparing the data. And then my other co-author, Renellys, helped me with the Glorious modeling project as well as other folks at Mercator Ocean. The loan context, it was made possible through a lot of people talking and coming up with ideas and letting generously donate to me. And then Paul Freitag at Aoml at the very last minute incorporated them into the morning so we could get the real-time data and not have to wait a year to get the data. You couldn't do this without publicly available data sets or without support from Siemens, without support from Siemens, Aoml, as well as various funding agencies. And that is it. Are there any questions?